At 11 o'clock. So last time we talked about the difference in displacement and distance traveled, and I said the next time we're going to do an example. So we're going to start off with this example. And see where that example went. Here it is. So example, we're looking at the velocity function to be t squared minus 2t meters per second. So if I want to find the displacement, from 0 to 3, I integrate it, right? So I'm finding the integral from 0 to 3 of t squared minus 2t dt. What is the antiderivative of t squared minus 2t with respect to t? Then I'm going to plug in my upper bound minus my lower bound, so I have 3 cubed over 3 minus 3 squared minus 0 cubed over 3 minus 0 squared. Does anyone have any questions at that point? All right, I plug in my upper bound minus my lower bound. So evaluating this, I get 27 over 3 minus 9 minus 0, which equals 0. If I find a common denominator, it would be 27 over 3. 27 minus 27, 0. 0 over 3 is 0. So it tells me the displacement would be 0. So I started at a position, I went somewhere, and I came back to that exact same position. Doesn't really tell me too much what happened. What was the total distance traveled? I'm going to have to integrate the absolute value of this. So that's part B. The distance traveled from 0 less than t, or 0 less than t less than 3. So now if I want to find the distance traveled, I'm integrating from 0 to 3 of the absolute value of t squared minus 2t dt. So I really need to know when's this function positive and when's this function's negative. So the absolute value of t squared minus 2t, well, this would be t minus 2. That would be the factors of that. So if t is less than 2, if t is less than 2, my function's negative, right? So I replace this with minus t squared minus 2t, right, if t is less than 2. If t is greater than 2, I just replace it with t squared minus 2t. So now if I want to integrate this, I'm going to have to break this up. From 0 to 2, I'm integrating this function, minus t squared plus 2t dt, plus the integral from 2 to 3 of t squared minus 2t dt. Right? Really what this is the change in position from s of t minus s of 0. And this is the change in position from s of 3 to s of 2, right? I just know that they're always positive, so I can drop the absolute value. So we did something similar to this in rectilinear motion when we first talked about it, 4.6. But now let's go through, from here. The antiderivative would be minus t cubed over 3 plus t squared. I'm going to plug into minus 0 plus t cubed over 3 minus t squared. I'm going to plug in 3 and subtract when I plug in 2. So this is minus 2 cubed over 3 plus 2 squared. minus a minus 0 cubed over 3 plus 0 squared. So I'm just being really careful here, right? I know this is going to evaluate to be 0. Pretty easy. If I plug 0 in here, it's 0. But I want to show you step by step where this is going. If you know this is going to be 0, you don't necessarily have to write out this. You can just say minus 0. Plus, this is 3 cubed over 3 minus 3 squared minus 2 cubed over 3 minus 2 squared. So simplifying some things here, I have minus 8 over 3 minus 8 over 3 plus 4 minus 0 plus 27 over 3 minus 9 minus 8 over 3 minus 4. So this is 0, and I also know this is 0, right? So here I have, if I need a common denominator, I multiply top and bottom by 3, so I have 12 minus 8. So that's 4 over 3. And then from here I have a minus 4 over 3, which would give me a positive 8 over 3. Do you see you have to be very careful with your negatives, especially when you have a negative of a negative. And if you would have got down here to be 0, you'd probably say, okay, something's off. I have to have some distance traveled. Or if you get a negative number, something's off, because the absolute value tells you your function is always positive. Amanda?
So the last part, when you do the second integral and you minus it, and then the plus t squared, or the 2 is becomes a minus because you're subtracting the a.
So, do you understand this line?
Yes.
Okay,
And then
so when I plug in 2,
why did you do a minus t squared up there? Plus t squared.
this minus,
Yes.
that came from evaluating the integral. This is a negative. Make sense? Because when I have a negative out front, I have to distribute to both of them. So this would be a minus t squared plus 2t. So when I integrate that, I have a minus t cubed over 3 plus t squared. But when I integrate this function, I get a positive t cubed over 3 minus t squared. Because the integral of a minus 2t is minus t squared. It does not click? Sure. Any other questions? So I'm going through and I'm showing this probably more detail than what you would need to. Right? Clearly this goes to 0. Maybe not so clear if this goes to 0. But you have to be very careful. I plug in 2. I want to make sure I have this negative here. I can't pull this negative out front unless I pull it out of both terms. So a lot of times when you get long polynomials, you have to be very careful when you plug in the first one minus the second one. You want to make sure your parentheses are very well defined. Or when you just plug that in your calculator, it can mean a bunch of different things if you don't have the right parentheses, and you can be off. Question?
If there were more than one solution to that t squared minus 2t equals 0, you could potentially have several different equations.
You could have several different intervals, yes. So what you could do is say, okay, I'm gonna find the area underneath the curve from 0 to 2. When you do that, it will be negative. You can just make that positive. But you have to be very careful about doing that. Right? So if I find this area and I don't make it negative, if I integrate t squared minus 2t from 0 to 2, I'm going to get a negative 4/3. But if I want the absolute value of that, that's really positive 4/3. But you can't just drop the absolute value on the whole interval from 0 to 3. You could pull the negative out front and deal with that later. And when you get the negative integral, then pull the negative through and say, oh, well, it's really positive, though, because I'm looking at the absolute value. So this is just an example of how to apply the calculus. I cannot drop the absolute value. If I drop the absolute value on an interval in which my function is negative, I have to replace that with negative function. I can drop the absolute value on an interval in which my function is positive. Right? So just a quick example of what I've seen come up in the past. If I ask you to integrate from 0 to 20 of the absolute value of x minus 10 dx, how would I split this up?
0 to 10, 10 to 20.
Yeah, from 0 to 10, what would I replace here? Negative x minus 10 dx plus from 10 to 20 of just x minus 10 dx.
That was just by solving the absolute value for your positive.
Because I know this equals 0 at 10, and so less than 10 it's negative, so I replace this with a negative. You could say, well, I'm going to take negative the integral from 0 to 10 of x minus 10 dx plus 10 to 20 of x minus 10 dx. So you have to be careful when you do this because this negative is going to be out front of x squared over 2 minus 10x from 10 to 0. Do you see how this negative is out front of all of this instead of just being distributed through that? If you want to do it that way, perfectly fine. Be very careful, though, you're distributing the whole thing. Right? This would then be the same 20 to 10. But this area is going to be a negative area. When I plug this in, I'm going to get a negative value. And then so the negative negative gives me a positive. Right? Because 10 squared is 100 over 2 would be 50. Minus 100 would be minus 50. But really the area is positive 50, so that negative's out front. Okay, so I think that is enough of 5.7. 5.8 is pretty short. So we're going to talk about 5.8. My notes are all out of order here. Okay. So 5.8 is getting to this idea of the average value of the function and talking about the average value or like the average velocity. So 5.8. Value of a function and its applications. We don't get into too much of the applications. So average value. The average can be found by taking the position at 1 minus the position at 0 divided by the time at 1 minus the time at 0. Right? You guys have probably done this since middle school. If I traveled 50 miles in an hour, the average velocity I had to be going was 50 miles an hour. I start out going 3 miles an hour, then I might go 60 miles an hour, then I might go 2 miles an hour, but my average velocity over that interval would be the distance traveled divided by the time. So this is over some interval t0 to t1. So this is with something that means something, velocity and position, right? So it turns out another way to write this in calculus would be 1 over t1 minus t0, the integral from t0 to t1 of the velocity function. which this leap shouldn't be too hard to make, right? If I integrate velocity, I get position. If I plug in my upper bound minus my lower bound, I get my change in position. Change in position divided by time is the average velocity. So if we look at a quick example, the velocity function is 2 plus cosine of t from 0 less than t less than or equal to pi. And I want to find the average velocity. So the V average is going to be 1 over pi minus 0, the integral from 0 to pi of 2 plus cosine of t dt. Right? Just knowing that you integrate the function and divide by the interval to get the average value of that function. So if I do this, I have 1 over pi, 2t plus sine of t from pi to 0. 1 over pi, 2 pi plus sine of pi minus 2 times 0 plus sine of 0. Sine of pi? 0. Cosine of pi is 1. No, cosine of pi is minus 1. Sine of pi is 0. 2 times 0 is 0. And sine of 0 is 0. So we get 2 pi divided by pi, which is 2, right? So this might mean something like meters per second. Let's pretend like it is meters per second. Feet per hour, kilometers per hour, miles per hour, whatever the unit of measurement for my original velocity is. This would be the average velocity. This is from the formula for V average. V average is going to be the change, 1 over the change in time times the integral of the function.
You integrated the cosine, right?
Yes,
But why didn't you integrate the 2t?
because I have to integrate the whole function. So what's the integral of 2? 2t. What's the integral of cosine? Sine of t. So the position function, given this velocity function, the position function is 2t plus sine of t. So you have to integrate both of them.
Okay.
Did you cancel out that pi?
This pi, yeah, 2 pi divided by pi is 2. Yeah. They cancel. So 2 pi over pi is just 2. So really, there's nothing new here except the concept that once you integrate this function, you divide by the interval, the length of the interval. That's going to give you the average value of the function. They introduced this idea of the average value of the velocity function. What's the average velocity? The average acceleration, the average income, the average revenue. Whatever function you have, you can find the average value of that function by integrating that function and dividing by the length of the interval. So this is the idea of this average value, it's not a t, of a continuous function. So the average value of a function is a continuous function on a to b. So it's b minus a, the integral from a to b of f of x dx. This would be f of t dt, f of p dp, whatever your variable is. Generally we like x in calculus, but a lot of times in physics we like t. We like to think about things with time. Question?
Where you talked about with velocity, you integrate
Mhm.
and get back to your position function, it's going to be position over a certain amount of time to
Yes.
give you your average.
Yes.
So in order to do the acceleration, do you have to
Well,
double
the-
integrate to get back to your position function?
The average acceleration is the change in velocity over time.
Okay.
Right? If I
Okay,
say I
understand.
accelerated an average of 2 miles per hour, so I might have started out and then I'm increasing speed.
Okay.
So it's not as common to see. I mean, velocity is something that we know what that means. But the change in acceleration might not be as straightforward of saying I'm going from 0 to 10, so I had to accelerate.
Okay.
My average acceleration would be the change in acceleration divided by the time it took me. So a lot of times when they sell sports cars, you know, they go 0 to 60 in. That's an acceleration feature, right? I can go 0 to 60 in 3.2 seconds. That's an average acceleration. Question?
I don't understand how finding the average velocity is getting it to position.
No, integrating velocity gives you position.
Exactly. So, why,
So-
how do you find the average velocity from changing it back into position?
So if I went 60 miles in 1 hour, how fast did I go? Do my change in position, which would be 60 minus 0, divided by an hour minus 0. An hour. Or 60 minus 0, right? So that would be 60 miles an hour. Your change in position divided by your time is your average velocity. Change in position over time is average velocity. So if you integrate velocity, you get position.
And then you're
You change in position would be your upper bound minus your lower bound. So it's the same thing as what I'm trying to equate. I might not give you a position function. I might give you a velocity function, ask for the average velocity. I might give you a revenue function and ask for the average revenue over some time interval from 0 to 6 months. How much money did I make based on this function? What was the average income over this time interval? So you can do it, so much money per month. You can do so much money per day, depending on what they want there. So this is kind of the formula for the average value. You take 1 over the length of the interval times the integral of the interval. The integral of the interval. So I always get kind of tongue-tied there. So this is going to lead us to the mean value theorem for intervals. So mean value theorem for integrals. So what this is saying, this is theorem 5.8.2. If f of x is continuous on a closed AB, then there is at least 1 point, we'll call it x star, in AB, such that the integral from a to b of f of x dx equals f of x star times b minus a. So this average value can be found by taking 1 over b minus a, the integral from a to b of f of x dx. This is the average value. Let's see. I'm just kind of elaborating on it. This is the average value of the function. The x star is the element in the interval from a to b at which the average value occurs. The average value occurs. So graphically, sometimes, if we look at this graphically, it might help kind of make sense. This is f of x. Let's say this is from A to this is B. There's some point in here, x star, that f of x star is this average value. So if I take the average value times the length of the interval, I get the area underneath the curve. It equals the same. So you see here, I'm underestimating, and here I'm overestimating, so it equals out. So the mean value theorem for integrals states that if you find the average value, you set the function equal to that, and you find this magic x star point that gives you the average value.
Is that always an inflection point?
No, it's not going to be an inflection point.
So it's f of x.
So this height is f of x star, which is the average value. If I take the average value times the length of the interval, I'm going to get this area. This area is the same area as the area underneath the curve of the function from A to B. There's some point in there that's average. So if I take the average value times the interval, I get the area underneath the curve. So let's actually do an example of this, of applying it in a real problem.
So the area of that box basically is the same area.
Yes.
Fine.
So let's look at the example, the square root of x from, I think, 1 to 4. Okay, so find the average value of f of x equals the square root of x over 1 to 4, and all points at which the value of the function is the same as the average value. So if I look at graphing y equals the square root of x, I have this function. I'm going from 1, 1 to 4, 2, right? I want to find the average value of this function in this interval. So if this is 1 and this is 2, and this is y equals 1 and this is y equals 2, my average value has to be between 1 and 2. Make sense? My point in which my function equals the average value has to be between 1 and 4. That should be 4. Sorry, 1 and 4. Now let's just write this better. 4. So first off, I have to find the average value. So I take 1 divided by 4 minus 1, the integral from 1 to 4 of the square root of x dx. This is the average value. So I have 1/3 2 times x to the 3/2 over 2, and I plug in 4 and I subtract 1. So I have 1/3 2 times 4 to the 3/2 over 3 minus 2/3 times 1 to the 3 over 2. So 4 to the 3/2 would be the square root of 4 cubed. The square root of 4 is 2, and 2 cubed is 8. So this is 16 over 3 minus 2 over 3, which gives me 1/3, 14 over 3, which gives me 14 over 9. So the average value is 14 over 9. Make sense? Question?
When you're doing, this is just a general question, but when you're doing them on intervals like 1 to 4, and
Yes.
then you're subtracting, but then when you are doing 2 different intervals, you're adding, right?
Correct.
Okay.
Yeah, so the fundamental theorem of calculus says the integral of a function from a to b with respect to x is going to be the antiderivative at b minus the antiderivative at a. But if I want to find the area of multiple intervals, I'm going to add those together. So if I ever have to split up into 2 integrals, I add them. Okay, so I get 14 over 9. So now I want the x star point that gives me f of x star equals 14 over 9. So I'm looking for when does the square root of x star equal 14 over 9. So if I square both sides, it turns out x star equals 196 over 81. 196 over 81, 196, 96, not 98. 196 over 81 is about 2.4. 14 over 9 is approximately 1.55. Just let that repeat. So that makes sense, right? The value of the function from 1 to 2, the y point being 1 and the yp being 2, the average value is about 1.55. And that happens at when x is 2.4, approximately. X star is 2.4. Does that make sense? The application of that? So it is also saying that if I want to integrate from 1 to 4 of the square root of x dx, I can take 14 over 9 times 3, which would get 14 over 3, which would, we already knew that, right? We already did that work to show that.
So what was x star, like the x star?
This x star is this point in which the function, this is x star, the point in which the function equals the average value. So then if I take the average value times the length of the interval, I get the area underneath the curve, which is the same as the integral. It's just an application of the theorem. They might ask you to find the x star. The key here is do not differentiate the function. Remember the mean value theorem? The mean value theorem and Rolle's theorem says the slope of the secant line is equal to the slope of the tangent line at a point. This is different. This is saying that the average value of the function, that there has to be some point on the interval which the function equals the average value, not the derivative of the function. Question?
So the x star is, the x value is the 1.55, the y value?
Yes, that's the average value. This 1.55 is right here at x equals 2.4, y equals 1.555. That's the x value is where the coordinate. The x value is where I'm plugging it into the function, the y value is what I'm getting at. So yeah, this is the average value, which would represent the y value, and this is where it happens at.
Okay.
And there can be multiple points. There can be multiple points in which the function reaches that average value. It turns out if it's linear, it's right in the middle, which makes sense on your interval. Okay, so that,
14 over 3.
this is just the area from 1 to 4, which you can take the average value times the length of the interval. This is just algebra rearranging this, right? The average value represents 1 over the length of the interval integrated over that interval. If I wanted to then solve for the integral part, I multiply the average value by the length of the interval. Right? I can just rearrange those, right? The average value of the function, go ahead and write this out, equals 1 over b minus a, the integral from a to b of f of x dx. If I want to solve for this, I multiply both sides by b minus a. So that tells me that the integral from a to b of f of x dx equals the average value of the function times b minus a. So if I give you the average value of a function on an interval, and I ask you to find the area underneath the curve, it's really easy. You don't have to integrate. You just take the average value times the length of the interval. That is the area underneath the curve.
So if you give a linear function, it should give you the same answer as doing the midpoint.
Yes. The midpoint in terms of x and the midpoint in terms of y, yeah. Right, because the rate of change is constant. But in the square root of x, the rate of change isn't constant, right? Because if you look at the slope is 1/2 x to the minus 1/2, so it depends on x. As x gets really, really large, the slope is decreasing, so the rate of change is decreasing. So you have a lot of change at first, and then it slows down. So the average value is going to be closer to the 2 than it is the 4. And it turned out to be 2.4. So it's on this side of the 2. Right? So the midpoint between 1 and 4, well, that would be 0 to 4. The midpoint would be 2. So 1 to 4, 1.5, so 2.5. Yeah. So that's closer to that side, the average value. And if I extend this out, the average value would then just move along with that. Okay, so that's really the only material in 7-8, is just this idea of average value, the average value of a function, the average velocity, and then the x star point in which the function equals the average value. So we're going to introduce 5-9, and I'm only going to probably have time for one example here. 5.9 is evaluating definite integrals using u substitution. So I said we would talk about this dummy variable u when we actually have bounds to deal with. And we're going to talk about two methods. Last semester, about half the class went with method 1 and half the class went with method 2. This semester, I asked the previous class and no one wanted method 1. So I don't know if it was just because they didn't want to raise their hand. But when you're evaluating a definite integral, when you need to use this u substitution, method 1 is going to be first evaluate the indefinite integral, which we've been doing. By substitution. Then use this idea that the integral from a to b of f of g of x, g prime of x, dx, is going to equal the integral of f of g of x times g prime of x, dx, and then plug in the upper bound and the lower bound. So we've dealt with problems like this, right? Where we have to do a u substitution, we do the u substitution, we get the integral in terms of u, we integrate that, we get the antiderivative in terms of u, then we replace, everywhere we have a u, we replace that with what the function is in terms of x, and when we get our antiderivative in terms of x. And then we use our x bounds, right? These are the bounds on x. So I can't plug that into the u function. So the key here is we don't have to modify the x limits of integration. Some students like this because they don't want to have to worry about changing the bounds. They don't want to have to worry about messing that up. They get their antiderivative in terms of x. They plug in their x upper bound minus their x lower bound, and they get an answer. Method 2, the key is actually changing the limits of integration and dealing with it in terms of u. So you're going to make the substitution. So u equals g of x, and then you're going to replace the x limits. So x equals a, you're going to change that to u equals g of a. And x equals b, you change that to u equals g of b. So now you're dealing with the integral from g of a to g of b of f of u du. So then after you integrate it, you have a function of u. You can plug in your u bounds. You don't have to go back to terms of x. I'll give you guys a minute to write that down. So we're only going to really have time for one example. So in this one example, I'm going to use both methods. So let's look at method 1. So if I want to integrate from 0 to 2 of x times x squared plus 1 cubed dx. Well, method 1 would tell me to change this to an indefinite integral, integrate that in terms of u, plug back in terms of x, and then deal with that and use my upper bound and my lower bound. So method 1 would say evaluate x times x squared plus 1 cubed dx first. So what would be my u substitution here? Yeah, x squared plus 1, right? So what is my du? 2x dx, right? So I have an x and a dx. So if I wanted 2 here to make it perfect, I'm going to have to pull out a 2. I'm going to pull out a 1/2, sorry. Because 2 over 2 is 1. I multiplied this 2 because that's exactly what I need to just replace that with du. So I have 1/2 the integral of u cubed du. Simple enough, right? Because 2 over 2 is 1. But I need this 2 inside here so I can replace it with du. If you don't like that method, you can always solve for dx. And dx is going to be du over 2x. So when I plug that in, the x is going to cancel and you're going to be left with a 1/2. Right? You guys see both techniques of doing that? Either way is fine. So does everyone see where that 1/2 came from? Because 2 over 2 is 1, but I'm going to pull this 2 inside here because I need a 2x dx to replace that with du. So integrating this, I have u to the 4th over 2 times 4. So really I have a plus c. So then I actually have an x squared plus 1 to the 4th over 8 plus c, right? But now I can just use the c to be 0 over here. This is going to be x squared plus 1 to the 4th over 8, and I'm going to plug in my upper bound minus my lower bound, right? So I get 2 squared plus 1 to the 4th divided by 8 minus 0 squared plus 1 to the 4th over 8. So this ends up with 78.
So all you're saying you do there is just integrate and then apply that you're bound.
Yeah.
afterwards.
So I said, let's pretend like bounds don't exist.
Yeah.
Oh, bounds. I find the antiderivative. Then once I find the antiderivative, I say, oh, let's find the antiderivative is the same as this function, but I'm going to plug in my upper bound in terms of x and my lower bound in terms of x. And really, if I'm going to drop down to the next page here, this is going to end up being 5 to the 4th over 8 minus 1 over 8, right? Which is 7 over 8. Our next integral will look like this. So I wanted to write that. So let's look at method 2. Method 2, approach for the u substitution part is similar. U is x squared plus 1, du is 2x dx. But now I'm going to change our bounds of integration. I'm going to say they exist. I have to deal with them. So this is saying at x equals 0, what would u equal? So I go to my relationship. If x is 0, what is u? 1. And if x is 2, what is u? 5. So I'm going to do the same thing I did here with the 2 and pull out a 1/2. So this is exactly du. So I have 1/2. But now my bounds are going to be u bounds. So 0 would be 1. 2 would be 5. So I'm integrating this from 1 to 5 of u cubed du. Du also tells me I'm integrating my u bounds. So I have to make sure that these are bounds on u, not on x. A very common mistake here is integrate in terms of u and don't change your bounds and plug in the wrong limits or the wrong bounds. So I end up with u to the 4th over 8. I plug in 5 minus 1. So I have 5 to the 4th over 8 minus 1 to the 4th over 8, which ends up with 78. Which is the same thing I had up here, right, from method 1. So you have your choice. Your choice can be, you can go ahead and do the u substitution and change your bounds in terms of u. When you integrate it, you don't have to go back in terms of x. You can leave it in terms of u and use your u bounds. Or you can integrate in terms of u, plug it back in terms of x, and use your x bounds. Does that make sense? So there's really not anything new now except we're evaluating using u substitution. We're evaluating the area underneath the curve on an interval. So we're actually applying this idea of this u substitution. I'm going to manipulate it to this dummy variable, but I can keep it in that dummy variable as long as I change my limits to that dummy variable. And then I'm perfectly fine. All right, we will cover a little bit more of this on Monday and go into chapter 6. So your quiz will be posted in about 15 minutes, and I'll also send an email when it's posted, and it will be due Sunday at 11 p.m. Enjoy your weekend.